Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Cross Flow Filtration, lecture number 2 on this cross flow filtration. We have already seen a few basic things about the cross flow filtration and different types of membrane properties. Those kind of things we have seen in our previous lecture. Now we are going to see a few more details about the cross flow filtration, especially with respect to ultrafiltration. So, we will be developing some equations for the flux, permeate flux, concentration, polarization, etc. For the case of ultrafiltration membranes. So, permeate flux of ultrafiltration membranes. So, the performance of a membrane in general can be characterized by three important points. First is the permeate flux, second one is the percentage rejection of the solutes by using the membranes, and then third one is the concentration of solute in the retentate stream, because here in the membranes one of the phase retentate phase become more concentrated compared to the feeds. So, what is the concentration of solute in the retentate stream is also kind of important factor, as we are going to discuss. We are going to find out each and every detail of these things now in this particular lecture. So, because of membrane fouling, the permeate flux often decreases, whereas the rejection may increase. What happens when there is a kind of membrane surface here, along with when a kind of feed which is having a small particle, a low concentration solution, which is feed is here nothing but a solution having low concentration of particles, and then particle sizes are also in general very small, of order of microns or even less. Then only we use this cross flow filtration using membranes. So, now when this separation is taking place, what happens? Some of the particles will be deposited on the layer, and then they form a kind of a very thin gel kind of layer here, right? Very thin gel kind of layer would be there, right? So, because of that layer, additional resistance to the flow of permeate to pass through this membrane would be there. Membrane resistance is already there, and then because of that one there is a kind of some permeate flux, and then but in addition to this membrane resistance, the gel layer, whatever the particles they are forming on the surface during the process of membrane separation. So, this gel layer will also be offering additional resistance. Because of that one, permeate flux would be reduced, but however more resistance is there and more particles would be retained towards the retentate side. So, then the rejection may also increase. Now, what we consider? We consider a performance of a clean membrane used for purifying a solution having certain amount of osmotic pressure. Okay. So, this osmotic pressure is function of concentration, as we understand. So, as the concentration of the solute increases, the osmotic pressure of the feed solution whatever is there, that increases. Okay. So, then accordingly the correction has to be made in the performance. So, all those things we are going to see now here. Now, let us assume the water is flowing through a porous structure of the selective membrane layer within the laminar flow. Not necessarily assuming, because in general whatever the flow is there through the membrane, that permeate flow rate is in general very small. So, the Reynolds number would be in general very small. So, under such conditions, laminar flow conditions or equations related to the laminar flow can be happily considered. And then driving force here for the performance whatever we are trying to develop, performance equation we are trying to develop for the clean membrane. For that case, driving force is not just the pressure drop, but the pressure drop minus osmotic pressure, because we are taking a case where the solution is having a significant amount of osmotic pressure, and then epsilon is the void fraction of the membrane. So, membrane in porous structure is there, whatever the porous structure void fraction is there, so that is epsilon. In general, pores are not uniform cross section, and then often they are interconnected, as we have seen several cases. Because of that one, whatever the nominal thickness of the active layer. So, let us say if this is the active layer, these active layers are in general in a few micron sizes, right? But just to explain, I am drawing a kind of thick layer so that we can see the details. So, this here this is the active layer, membrane layer. This is mounted on a kind of support, if it is a supported membrane kind of thing, and this support is a kind of a macroporous material. Okay. Now, here these pores, whatever the membrane surface onwards, the pores should be there. The pores not necessarily be a kind of uniform pore structure, something like this. It is not possible. So, they may have a kind of different degrees of interconnection, and then different levels of porous structures as across the cross section. If this is the L of the membrane, across the cross section of this active layer, as we pass on, the path that the permeate molecule is passing through the membrane, that is more than L, because the porous structure is not uniform like this. So, because of that one, we have to multiply by some tortuosity factor tau, as it is similar as kind of what we have done in the case of a flow through packed bed. Okay. So, here also the pores are interconnected and they are not uniform, and then their length, the molecule may be traveling the length more than the active layer thickness. So, L has to be multiplied by some factor, tortuosity factor, that is tau. Now, for this case, whatever the Hagen-Poiseuille equation is there, what we assume that we take this now L, if you multiply by tau, that tau is taking care of the tortuosity factor. So, now we can say that these pores are kind of a uniform cross section L tau, that tau is taking care of the non-uniformity factor. So, then through this pore, through individual pores, now each pore is like this of length L tau, and then permeate through which is coming V by epsilon, because there are n number of such kind of pores are there, right. So, similarly exactly the same way that we have done for the packed bed. So, these factors we have to bring into the picture in Hagen-Poiseuille equation. Whatever the delta P by L is equals to 32 mu V by d square is there. This is the Hagen-Poiseuille equation for flow through a pipe, uniform cross section pipe. So, then this is what we have Hagen-Poiseuille equation, which is valid for a infinitely long cylinder, or for the cylinder where the case L by D is very much higher than the 1. So, that is L is very much larger than the D. So, then it is valid. Under such assumptions, those assumptions we can also apply for the simplified case here, as we have given here, right. Okay. But with a kind of modification, this L has to be multiplied by tau, and then this V has to be divided by the epsilon in order to bring the effect of the voidage through which only the material is flowing, through which only the permeate is flowing. When we do this one, we get this thing. So, this is 32 mu V by d square is nothing but delta P by L, and then also this pressure, now the whatever the resistance is, the driving force for the flow is there, it is not a simple pressure drop, but also there is a kind of effect of osmotic pressure. So, that should also be taken in care into this equation. So, delta P minus delta pi divided by L has to be now L tau, 32 mu, V has to be V by epsilon, and D is as it is, we are keeping as it is, though it is not the same as a kind of this thing, equivalent diameter kind of thing we have to write, but let us not go into all those details, because we are not going to simplify this equation further anyway. So, what we get here, superficial permeate velocity normal to the surface V is nothing but delta P minus delta pi d square epsilon by 32 mu L tau, right. So, here the from this equation, though V is having the units meter per second. So, this is the permeate flux, but in general this permeate flux is also represented in terms of meter cube per second, meter squares, and not only just meter per second, they are just multiplied by some kind of factor, so that reported in this kind of forms, but more often the permeate flux is reported in terms of units liter per meter square hour, liter per meter square hour. Okay. So, now, but if you wanted to use this equation, let us assume you know the concentration, the solution concentration. So, then you can find out the osmotic pressure, that is not a problem. But what is the pores? This membrane is having several pores on the surface, right, and then these pores are having different cross sections. So, which diameter should you take? That you do not know. And then in general, voidage is also very difficult to find out, though you have the facilities now, you can find out for a given membrane, right. So, but it is not readily available, in a sense it is not readily available, though it can be measured. And then what is the tortuosity factor? We do not know actually how much it is. In packed bed we found for some cases it is 2.1, something like that is appropriate one, appropriate for laminar conditions, but other turbulent conditions it may be very much higher, very much different from the laminar case tortuosity factor. So, having these many ambiguities, getting a reliable information about permeate flux is going to be very difficult. So, what we do? We try to overcome these measurements of d, L, epsilon and tau, etc., and then rearrange this equation in a different kind of form. So, how we can write a different form? These parameters we can these characteristics d, L, epsilon and tau, etc., we can incorporate in kind of in some kind of permeability or in some kind of resistance. So, in two ways the permeate flux can be reported. So, now when you report, we can report in terms of the permeability, that is pure water flux at room temperature per unit pressure drop, or membrane resistance, which is reciprocal of Qm as below here. So, the same equation we whatever we have. So, V is equals to delta P minus delta pi, and then something is there, right. So, and then something is there, that like if you specifically the previous equation one, we write V is equals to delta P minus delta pi d square epsilon 32 mu L tau. This equation now we are writing for a pure water flux. Qm is a kind of for a pure water flux kind of condition. So, for pure water, if there is no solute, then there will not be any kind of osmotic pressure. So, then we can write this equation delta P multiplied by some constant. So, all these things are we measure, we incorporate or include in something like that Qm, that we can call it as a kind of permeability. Okay. So, or if you take the reciprocal of these things, so then we can take this one as a delta P by Rm. Rm is the resistance, which is the reciprocal of the permeability. So, the either of the way it can be written, either of the way it can be written. Okay. But in general, if you wanted to write the same equation for the case where you are using for purifying a solution, if you have a solution, there would be a kind of solutes, and then when there is a kind of solute particles in a solvent, then that that overall final solution would be having some amount of osmotic pressure. So, you have to incorporate that osmotic pressure also in a generalized equation, and then when we are doing the separation by using membrane for those solutions, then particles will be forming a kind of gel layer, not as a kind of cake as we have seen in cake filtration, but very thin gel layer kind of thing would be forming on the surface. So, that surface, that gel layer is also offering some additional resistance in addition to the resistance due to the membrane. So, then whatever the Rm is here is is resistance due to the membrane only. There is no resistance due to the gel in this equation, because this equation we have written for the pure water case. Pure water case, there are no particles, so there is no gel formation kind of thing. So, but when you take the solution, then this Rm should be added with the R gel or the resistance due to the gel, and then this delta P has to be subtracted with the osmotic pressure, that is minus delta pi should be added, that we are going to see, right. So, this equation, though we can write V is equals to Qm delta P, but it is writing delta P by Rm kind of form is going to be more useful, because wherever we have this kind of gel kind of formation things are there. So, those things can be easily incorporated their resistance can be easily incorporated if you are writing in the form of V is equals to delta P by Rm form. So, now generalized flux equation for ultrafiltration membrane should be what? It should be V is equals to delta P minus delta pi divided by Rm plus R gel, right. Okay. So, if you use the pure water, then delta pi is 0 for pure water, osmotic pressure is 0 for pure substance, and then there will not be any kind of gel. So, R gel would also be 0. That would be the case of previous case of equation number 2. But if you are using this one for purifying a solution using this ultrafiltration membrane, so then because of the particles in the feed solution, there will be a kind of osmotic pressure that should be brought into the picture. So, the delta pi has come into the picture, and then there will be a layer of particles, fine particles forming on the surface as a kind of layer that is known as the gel. So, that would also be offering a kind of additional resistance when we are using this membrane for purifying a solution. So, that resistance due to the whatever the additional gel has formed, that should also be brought into the picture. So, that is here. Okay. So, if you take the pure water case, delta pi and then R gel would be 0, and then equation 3 would be same as equation number 2 as we have just seen. But further what happens, at room temperature this equation is fine, okay. But above room temperature or for a permeate that is not pure water, then the membrane resistance can be corrected for the change in the viscosity. The change in the viscosity of the permeate with respect to the temperature can be brought in into the picture like this. So, Rm prime is equals to Rm mu by mu naught, whereas mu naught is a kind of viscosity of the permeate at room temperature, and then mu is the viscosity of the permeate at a higher temperature at which we are operating. Remember, the same equation number 3 in some books is also written in terms of mu terms will also be there. So, then accordingly the units would be changing in general. So, here Rm prime is corrected resistance and mu naught is viscosity of water at room temperature or whatever the solution that we have taken. Okay. So, now concentration polarization. Concentration polarization is nothing but whatever the gel formation is there, let us say this is the membrane surface active layer. Okay, when there is a cross flow of a feed solution having a low concentration of fine particle. So, this is flowing cross like this. So, then retentate are taken like this, and then permeate is collected through bottom like this. Okay. Now, this is containing fine particles. So, then particles are retained over on the surface, they are separated, right, and then almost clear or almost clear permeate is collected at the bottom. This will also be having some kind of solute because 100% rejection in general is not possible. So, permeate will also be having some solute particles, but very few particles, very less fraction would be there, right. And then retentate, it's a kind of concentrated solution. So, retentate concentration would be much more higher than the feed concentration. So, while this process is going on, the layer of the particles would be forming as a kind of a gel here, and then that will be offering a kind of a concentration which is very much higher compared to the bulk feed concentration. Let us say bulk feed concentration is C1. On the surface, if you take concentration is Cs, the Cs is going to be very much higher than the C1 because of this concentration polarization or because of this particle are forming. So, the particle are forming as a kind of gel. So, that gel increasing the solute concentration on the surface of the membrane, that is known as the concentration polarization, right. So, this Cs at the surface is much more higher than the C1. And then let us say permeate concentrate or the solute concentrate in permeate is C2. So, C2 is not 0, if it is 0 only when the 100% rejection is there, but 100% rejection it is in general not possible for any case. So, then C2 will also have some values, okay. And then retentate concentration, let us say C or something like that, that must be very much different. Now, because of this concentration polarization, whatever the flux is there, the flux gradually decreases or the pressure drop increases, okay. And then when the pressure drop increases, the Cs also increases gradually, okay. So these kind of phenomena occur for ultrafiltration membrane. So this concentration polarization concept we are going to see now, and then we are going to develop equation for this case, okay. So now osmotic pressure depends on solute concentration at membrane surface. So now what happens, if you obtain the osmotic pressure based on the C1, so that is not going to give the correct results, because the solute concentration is very much different on the membrane surface, or whatever the osmotic pressure is playing role in separation, that is playing role only at the surface, because membrane surface, because there only from there that point only separation is taking place. So when you calculate the osmotic pressure for the solution, you have to use the Cs concentration rather than the C1, right. So that is the reason the osmotic pressure though is very small for a kind of dilute solution, dilute feed solution you take, let us say very small dilution like 0.01 percentage of solids are only there in a kind of feed solution. Despite of that one, so in general when you say that 0.01 gram per liter of solutes in a feed solution, it's a kind of very small concentration. So then what you assume, that osmotic pressure is going to be very small, that can be neglected. But because of this concentration polarization, what will happen? No, the Cs is going to be much more higher, it is going to be much more higher than 0.01. How much higher, that is what we are going to develop equation to obtain this expression. So even for the dilute solutions, you cannot avoid considering the osmotic pressure, because the osmotic pressure is based on the Cs surface concentration, which is going to be much higher than the feed solute concentration C1, okay. So this concentration is often much greater than the bulk concentration C1, especially if permeate flux is high and then solute diffusivity is low. And then concentration just inside the pores, let us assume if it is Cm, pictorially we are representing, going to represent. Cs is the surface concentration here, just let us say the pore is starting here. So right at this point, at the just inside the pore, the concentration of the solute is again going to be different from Cs and C1, okay. What is that? We do not know, let us assume it is Cm, okay. And then surface concentration is Cs, which is much more higher than the feed concentration C1. Cm is definitely different from the Cs, but it is lower than Cs by a factor k, which is known as the equilibrium partition coefficient, right. Such kind of similar discontinuity would be there for the solute concentration, where selective layer joins the large pore support in general. So pictorial, if you see this concentration variation or concentration gradient for ultrafiltration membrane, so this is the kind of membrane surface towards the support, and this line is a kind of membrane surface exposed to the feed solution, which is going to be separated, right. So now this is the selective layer thickness, we do not know what it is, okay. We do not want to know as of now, it is L. And then the support is thickness of the support is much more higher than the membrane thickness in general. So this is the support. On this support there is a selective membrane layer is there, so that is this one. And then the feed solution is flowing along the surface like this, because it is a cross flow filtration, it is not dead end filtration. So then the solute concentration in the feed, that is in the bulk solution, is C1, right. But as the process moves on, so then particles will be deposited on the surface, on the surface of membrane. So because of that one, the surface concentration or the concentration of the solute on the surface is going to be much higher compared to the bulk concentration of the feed, because till this point there is no separation. There is no separation or concentration change supposed to be, but the feed solute concentration near the selective layer on the selective layer surface is going to be very much higher because of this gel formation or because of the concentration polarization, right. That concentration we call it as a CS at the membrane surface. And let us say this is the membrane surface, right. So, here on this membrane surface, on this membrane surface we have taken one particular pore. So, on the surface the concentration is CS, okay, but just inside the membrane pore, whatever the pore one selected pore we have taken, here the concentration is Cm, which is going to be less than the CS, which is going to be less than the CS, that is Cm, but it is definitely going to be more than the C1, more than the C1. So, this the levels C1 is at lower level, CS is the at a higher level, Cm is the between these two, but towards the C1, okay. And then towards the permeate, once this whatever the solution passes through here, so some solutes will also be passing through. So, then from here the permeate is collected. So, permeate is in general pure, almost pure, but not completely pure. So, there will be some solute particles. So, then solute concentration in the permeate side is C2. So, pictorially if you represent concentration polarization, this is what you get. So, now here what we can see, the concentration from the bulk, it is almost stable to certain distance, almost constant to certain distance, but after that it is gradually increasing and then increasing to the such high concentration like CS at the surface, right. So, now we can separate the distance in two parts towards the membrane. So, towards the bulk flow, fluid side, whatever the distance is there, you just leave it as it is. Let us say this point, from here the concentration gradually increases and then it increases to such large concentration as CS at the membrane surface. So, this distance you take it as a kind of delta, okay. It looks like 8 here, but it is a kind of a delta. So, this distance what we do, you take it as a kind of delta. So, at x is equals to 0, the membrane surface at x is equals to 0, what is the concentration here is CS. At x is equals to delta onwards and then towards the bulk side, what is the concentration is nothing but C1. These are the boundary conditions. So, now some changes, concentration change with respect to the distance is happening only from x is equals to 0 to x is equals to delta. So, what is that function we have to find out if you wanted to find out whether CS, okay. So, that is what we are going to do anyway. Now, in general for cylindrical pores and then spherical molecules, whatever the partition coefficient K is there, that is given as 1 minus lambda whole square, where the lambda is the ratio of molecule size to the pore size. Lower the value of K, higher is the rejection in general, but however effect of wall friction on solute diffusivity also cause the rejection to become quite high even when the molecules are less than the half the pore size. That is, even when lambda is less than half, what happens, there is a kind of wall friction on solute diffusivity, effect of wall friction on solute diffusivity is there, that makes in this rejection very high even when this lambda value is less than half. Further, osmotic pressure of solutions of polymers, proteins and other large molecules increases significantly with the concentration. So, osmotic pressure, what if you calculate based on the C1, that is phase concentration, that is not going to give correct thing, because this delta pi in general increases for any of these polymer solution, protein solutions etc., with increasing the concentration. So, at the surface the concentration CS is much higher than the C1. So, whatever the osmotic pressure using this CS concentration is there, that is going to be the correct one, okay. This indicates what we indicate, that delta pi, a significant fraction of delta P should be considered even when the osmotic pressure of feed solution is negligible. Even if osmotic pressure of feed solution is negligible, because C1 is very small in general, Despite of that one, delta pi has to be incorporated in this equation, because what happened in the ultrafiltration membranes, there because of the concentration polarization, surface concentration gradually increases, okay, and then it reaches certain maximum concentration for a given thickness of the feed layer. Okay. At that maximum concentration Cs, this osmotic pressure is going to be much higher compared to the osmotic pressure calculated based on the feed concentration. So, because of that reason, even if the feed solution osmotic pressure is negligible, the delta pi has to be incorporated in the equation. But on the other hand, in general, in reverse osmosis, concentration polarization is treated using simple mass transfer equation, that is equating the diffusion flux to amount of solute rejected per unit membrane area. That is itself is satisfactory, where surface concentration is only moderately higher than that of bulk. Right. In reverse osmosis also such kind of concentration polarization would be there, but there we do not need to worry about variation of concentration with respect to the x distance from x is equals to 0 to delta, because the Cs and C1 variation is in general very small in the case of reverse osmosis. Like Cs minus C1 is very small, that can be in general neglected in the case of reverse osmosis. So, then you do not need to find out how this Cs is changing from Cs to C1 as x is increasing from x is equals to 0 to x is equals to delta. That you do not need to do in case of reverse osmosis, because that difference is very small. But in ultrafiltration, that is going to be very significant one. So, we cannot avoid that variation, whatever the concentration variations with x direction near the surface, we cannot avoid in ultrafiltration. So, that is what we are going to do now. So, for ultrafiltration, large change in concentration near the surface requires integration to obtain concentration profile. So, if you want to integrate, you have to develop a kind of differential equation that you can get by doing the basic balance equation. So, what kind of balance that we can have near the surface, membrane surface? Flux of solute due to convection plus diffusion is constant in the boundary layer, and it is equals to the flux of solute in the permeate. So, let us say if I redraw, this is a kind of membrane surface, right, this is a kind of support, and then here we have a kind of permeate of concentration C2. So, on the surface here the Cs concentration is there, and then at the bulk C1 is there. So, in this distance x is equals to 0 to x is equals to delta, the concentration is changing from Cs to C1. So, this variation whatever is there, that we have to take care, and then where the convection and diffusion both are taking place. So, whatever the near the surface, right, in the that is in the boundary layer, this boundary layer delta. So, within this boundary layer, whatever the flux, solute flux is there because of the convection and diffusion, that should be equal to the flux of the same solute in the permeate. Okay. That will give you the basic flux balance at the membrane surface. So, in the boundary layer, the solute flux due to the convection is Vc, and then in the boundary layer, the solute flux due to the diffusion is dV dC by dx. Let us take dV as a kind of diffusivity, and then solute flux in the permeate side is Vc2. And then what are the boundary condition? At x is equals to 0, that is on the membrane surface, C is equals to Cs, and x is equals to delta, that is the outmost layer of the boundary layer, whatever the concentration polarization, because of the concentration polarization whatever the boundary layer is formed, that thickness is delta. So, outer layer of that the boundary layer is exposing towards the bulk fluid. So, the concentration should be C1. So, from this point onwards concentration is everywhere, here it is C1. Okay. So, now this equation you solve and then apply these boundary conditions. So, then you will be having an expression to get Cs as function of C2. That is what we are going to do now. So, Vc plus dV dC by dx is equals to V C2, that we have done just now flux balance equation at the membrane surface. So, then now V terms we keep one side, other terms we take to the remaining right side, right. Now, we can rearrange this equation. V by dV dx is equals to minus dC by C minus C2 when you integrate either side. So, dx is integration of dx is x, and then x is varying from 0 to delta, that is within the boundary layer, okay. Due to the concentration polarization, whatever the boundary layer is there, that the thickness is delta, and then that is varying between 0 to delta from membrane surface to outer towards the feed side, okay, bulk solution side. And then minus dC by C minus C2 is nothing, when you integrate you will get minus ln C minus C2, and then surface concentration at x is equals to 0, concentration is Cs, at x is equals to delta, concentration is nothing but the bulk concentration C1. So, when you apply these boundary conditions, limiting conditions, we have V delta by dV is equals to ln Cs minus C2 by C1 minus C2. So, this is the equation. Now, here if you know the diffusivity and then thickness, boundary layer thickness, then you can know the Cs, because C1, C2 are known, the feed solution concentration you know, and then permeate solute concentration also you know while doing the experiment. So, Cs you can know from here. The same equation, if you rearrange this, dV by delta is having a kind of a meter per second units. So, that is we can call it as a kind of a mass transfer coefficient Kc. So, ln Cs minus C2 by C1 minus C2 we can write it as V by Kc. dV by delta has units of length per unit and is defined as the mass transfer coefficient Kc. Okay. This is the case when the rejection is partial. Indeed, in reality, most of the cases the partial rejection only takes place, complete rejection never takes place, very rarely it takes place, right. So, in case if you have a kind of a complete rejection, then C2 should be 0 in the same equation, then ln Cs by C1 should be equal to V by Kc. For simple case of complete solute rejection, which is not possible in general. However, if you have a case where complete rejection is taking place, then C2 is equals to 0, and then in above equation ln Cs minus C2 by C1 minus C2 is equals to V by Kc. If you substitute C2 is equals to 0, then we have V is equals to Kc ln Cs by C1. Okay. So, now what we understand further, permeate flux is non-linear function of delta P due to this concentration polarization, and a trial and error solution is needed to calculate V for a given delta P. Actually, if it is pure water, then water flux linearly increases with the delta P. But if you have a dilute solution which you wanted to purify by membranes, by using membranes in this ultrafiltration, then that flux of the solution it is non-linear, okay. We are going to see that one also. So, however, when there is a complete rejection of solute and no gel resistance is there, delta P for specified V can be obtained directly by using equation 7. From here you can get the Cs, and then once you know the Cs you can know the delta pi, and then once you know the delta pi, so then we can use this equation to get delta P for a required V. Basically what this statement says, that let us say if you wanted to have 0.001 liter per meter square hour of permeate flux, how much delta P should you apply? That is what you wanted to calculate. Okay. So, then for that you need to know delta pi also, how much delta P is required. If you want to calculate how much delta P is required for a specified permeate flux, let us say 0.001 liter per meter square hour of permeate flux, if you want to obtain by using ultrafiltration membrane, then how much delta P should you apply? That you can calculate by these equations, right. For that you need delta pi. So, this delta pi can be obtained by the Cs concentration, and Cs you can obtain from equation number 6 or 7 depending on the rejection. If the complete rejection, then equation number 7 can be used. If partial rejection, then equation number 6 can be used. That is the point of using this equation. So, this developed equation is used in two ways. You can directly obtain what is the surface concentration or the solute concentration at the surface CS, or you can obtain delta P required to maintain a specified permeate flux. Either way you can use these equations. Now, let us say as I mentioned already, whatever the flux is there, if it is for the pure water, it is going to be linear in general. So, but if you have a kind of a solution, if you have a kind of a dilute solution and then using a membrane for separating that solution, so that you can have a kind of clear permeate and then concentrated retentate as a kind of separate layer, then this flux is not going to be linear with delta P. Why? Because there is a kind of osmotic pressure because of the solute particles, right. Because of that osmotic pressure, even if you apply certain pressure initially, so for initial certain delta P there will not be any kind of flux. Now, here you can see at the origin this pure water flux is passing through the origin, but the other line, the solid line, is a kind of permeate flux for a kind of a solution. When you take a dilute solution, then the flux would be having like this, and then this is not passing through origin. That means the solute retention will be there, and then permeate flux will only start after certain delta P has to be applied, and that delta P is nothing but what that is, osmotic pressure has to be overcome, then only the flux permeate flux will start coming out, okay, or the permeate will start coming through the membrane. Until that pressure, until and unless that pressure is crossing that osmotic pressure, the separation will not take place. So, this is the reason here it is not passing through the origin. So, permeate flux of pure water feed is proportional to delta P, and then you can see this proportionality, a kind of linear plot you can see here, okay. So, this is increasing with increasing the delta P linearly. But for dilute solution, permeate flux is 0 until pressure drop exceeds small osmotic pressure. Whatever the small osmotic pressure is there, because of the presence of solutes in the solution, there is a small osmotic pressure. Until and unless the applied pressure exceed that osmotic pressure, the permeate flux will not be there, it will be 0, okay. Then after that, after crossing this osmotic pressure, further if you increase the pressure, right, when you start applying the pressure, gradually you increase the pressure, right. So, there will be a position, there will be a kind of pressure drop which is equal to the osmotic pressure, and then after that permeate is started coming. But after that osmotic pressure, if you further increase the applied pressure, then what happens? Let us say 1.1 is a kind 1.1 atmosphere is a kind of osmotic pressure for a given solution. Then up to 1.1 pressure drop, there will not be any permeate, and then permeate will be 0, and after 1.1 atmosphere is further gradually you increase the pressure drop, the flux is going to increase gradually, but this increase in a kind of non-linear like this, and then after certain point, let us say from this B to C point, it is going to be constant. That is the point where gel formation is there, and gel is offering a lot resistance, and that resistance is known as the delta P gel, which is not allowing further flux increase. With increasing delta P, CS increases, right. CS, that is the concentration, solute concentration on surface increases, because more and more particle would be forming or contributing towards the gel formation. So, CS concentration would increase, but CS concentration may be slightly increasing, but the corresponding osmotic pressure, you can see it is largely increasing. How largely it is increasing from one level to the other level gradually, you can see. So, that this is all delta P. So, as a pressure drop increases, the osmotic pressure is increasing to the larger extent, faster rate increases. This is the permeate flux versus pressure drop plot for a kind of ultrafiltration membrane. In general, this is what you find, okay. This maximum flux whatever is there, that is reached when Cs becomes equal to the solubility and a precipitate or gel layer forms at surface for some cases. But however, in some cases Cs at maximum flux is less than the solubility, as the rejected molecules form a surface layer with appropriate hydraulic resistance, which is because this whatever the particles are there, tangled mass of overlapping molecules at the membrane surface, they cause a kind of increased rejections for these kind of cases where the maximum flux is attained and then Cs is less than the solubility. Despite of that one also rejection increases. So, now what we understand here, so whether the gel formation is there or not, R gel and delta P gel can be applied to this layer even when there is no gel present, because the gel formation is going to take place gradually with increasing the delta P. So, flux is limited by the rate of mass transfer back to the bulk diffusion upon reaching that maximum flux. After this point, whatever the flux is there, here it is controlled by the mass transfer. Okay. Further, sudden increase in delta P, say from that point B to C in the picture we have seen, that provides a temporary increase in permeate flux, but it decreases to maximum steady state value as gel layer becomes thicker, because thick gel layer compresses with time and increasing the pressure drop would eventually decrease the flux only. So, this is about the concentration, polarization and permeate flux for the ultrafiltration membrane, and then how the permeate flux is changing with the pressure drop, etc. Those kind of things we have seen about this ultrafiltration membrane. So, in general these ultrafiltration membranes are used widely in food processing and pharmaceutical industries to separate and concentrate solutions of proteins or drugs. UF is also used to recover chemicals in the textile and paper industries as well as in waste treatment and water purifications. We have seen a few specific applications in the previous lecture, and then some generalized applications are given here for ultrafiltration membranes. Now, what we do based on this permeate flux and then concentration polarization concept for ultrafiltration membrane, whatever we have seen, we try to solve couple of problems. A tubular membrane with a diameter of 2 centimeter and water permeability of 250 liter per meter square our atmosphere is being used for ultrafiltration of cheese V at room temperature. The V proteins have an average diffusivity of 4 into 10 power minus 7 centimeter square per second, and osmotic pressure is given by this equation, where C is the protein concentration in grams per liter. The mass transfer is described by the Sherwood number, and Sherwood number as function of Reynolds number and Schmidt number is given here. So, now for the conditions of protein concentration 10 grams per liter, that is the C1 is given, and then solution velocity 1.5 meter per second, and gel concentration, that is Cs is given 300 gram per liter. C1 is 10 gram per liter. So, now you can see Cs is 300 gram per liter, 30 times higher, okay, and 100% rejection is there. So, under such condition, what is the permeate flux and what delta P should be applied to achieve this permeate flux? So, we need some kind of properties such as density and viscosity. So, for that, bulk solutions have the same density and viscosity as of water at room temperature, that we can assume as per the problem statement. Okay. So, we need to find out what is permeate flux and then what is pressure drop to maintain this permeate flux under 100% rejection conditions, right. So, Cs, we have this V by Kc is equals to ln Cs by C2. From here we can find out this V, but Kc we have to find out. How to find out the Kc? Kc we can find out from this Sherwood number expression. So, Re you can calculate because the solution velocity is given, density and viscosity of the fluid is given same as the water. Schmidt number also you can calculate. So, then Sherwood number you can calculate, from Sherwood number you can calculate the Kc value. Once Kc is known, from this equation you can calculate the V, because Cs is also given, and then C2 is 0, this is ln Cs by C1. So, d is 2 centimeter, V bar is 150 centimeter per second. This V bar is not the permeate flux, it is the velocity, it is the velocity of the fluid that is given. For the condition of protein concentration 10 gram per liter, solution velocity is 1.5 meter per second. At that high, whatever the across the membrane surface feed is coming at high velocities, right, that high velocity is nothing but 1.5 meter per second, it is not the permeate flux. Okay. So, 1.5 meter per second, I will write 150 centimeter per second, because we will be solving this problem in CGS units. At 20 degrees centigrade, water has the 1 gram per cc density and 0.01 gram per centimeter second viscosity. So, Re is d V bar rho by mu, d is 2, V bar is 150, rho is 1, mu is 0.01. So, Re is coming out as 30,000. Schmidt number is mu by rho d naught. So, which is given as a kind of mu is given as 0.01, d naught is 4 into 10 power minus 7, and then rho is 1, all are in CGS unit. So, it is coming 25,000. So, the Sherwood number, it is given as like this in the problem. So, in the Sherwood number expression you substitute Schmidt number and Reynolds number. So, you will get Sherwood number is 3.9 into 10 power 3, which is definition of the Sherwood number is nothing but Kc d by d naught. D naught is the diffusivity. So, now from here you can find out the Kc. Kc is equals to 3.9 into 10 power 3 into diffusivity is 4 into 10 power minus 7 divided by 2 is the diameter. Then you will get K as 7.8 into 10 power minus 4 centimeter per second. Kc you will get it as 7.8 into 10 power minus 4 centimeter per second. So, permeability Qm is given as 250 liter per meter square hour atmosphere. So, that we have to convert into the centimeter per second. So, then you will get this one, and then V is equals to Qm delta P, Qm delta P minus delta pi we have to have, because now it is a dilute solution. Dilute cheese V solution. So, delta P minus delta pi should be V by Qm. So, V is the whatever the permeate is there, that we have to find out, and then Qm is the permeability, that is 6.9 into 10 power minus 3, that is again given. Okay. So, now in this equation if you wanted to find out V, you need to find out delta pi, you need to find out delta P also. Okay. But for 100% rejection case, we know that V is equals to Kc ln Cs minus C1. So, we do not need to find out V from here, we can find out from here, because it is given in the problem statement for 100% rejection conditions. So, from here V you will get Kc, that is 7.8 into 10 power minus 4 centimeter per second, ln Cs is 300 gram per liter, C1 is 100 gram per liter given in the problem. So, then you will have this 2.653 into 10 power minus 3 centimeter per second as a kind of permeate flux. So, permeate flux is known. So, now V is also known from here. So, now you need to find out what is delta P. For that you just need to find out delta pi. Delta pi osmotic pressure expression is also given. In place of C you have to substitute Cs values, because we wanted to know the osmotic pressure at the membrane surface. At the membrane surface the concentration is Cs. So, 300 when you substitute here in this osmotic pressure equation which is given, then you will get osmotic pressure as 3.3 atmosphere. So, delta P minus delta pi is equals to V by Qm, and then V is now already 2.653 into 10 power minus 3 that we have calculated. Permeability Qm is given as 6.94 into 10 power minus 3. Osmotic pressure you just calculated as 3.3. So, 3.683 atmosphere of pressure drop you should apply if you wanted to have a kind of 100% rejection with permeate flux 2.653 into 10 power minus 3 centimeter per second. Okay. We take another example problem. A membrane filtration process is used to concentrate a suspension of 8 micron spherical particles, has a permeate flux of 150 liter per meter square hour at 30 degree centigrade and a pressure drop of 2.1 atmosphere. Under the same conditions, the water flux is 280 liter per meter square hour. Calculate the resistance of the membrane and the gel layer, that is Rm and then R gel we have to find out. In addition, we have to find out how thick a layer of particles would be needed to account for the gel layer resistance if epsilon is 0.4 and then mu is 0.801 Cp, that is L we have to find out. That is L is like on the membrane, this is the membrane, okay. On this membrane the particles gel layers are the particles are forming a kind of gel layers, right. What is the thickness of this gel layer? L. This we have to find out. So, for this we can use the Kozni-Karman equation, that kind of form, that delta P by L is equals to from the Kozni-Karman equation we have that 150 mu u 1 minus epsilon whole square divided by pi s square dp square epsilon cube. That expression we can use, right. So, in that expression delta P is known, only L that we can know. L is nothing but the length of the packing. Now, here that length of the thickness of the gel whatever is there, that is L here in this case, okay. So, before that we have to find out Rm and R gel. Let us see that one. dP is given, permeate flux is given, so we converted in meter per second. Delta P is given, it is converted into the Pascal. Water flux is also given in liter per meter square hour. If you convert into the meter per second units, it comes like this. Epsilon is given, mu is given, okay. So, in kg per meter per second, it is 0.801 into 10 power minus 3. So, then pure water flux is nothing but delta P by Rm, right. So, from here delta P is given. So, Rm should be delta P by pure water flux. Pure water flux is also given. So, delta P is nothing but we converted in Pascal. So, it is 2.1 atmosphere, but in Pascals it is 2.2287 into 10 power 5 Pascals divided by the permeate flux is given in pure water, it is pure water. So, pure water flux is given in liter per meter square hour. In meter per second, if you convert, it comes out to be 7.77 into 10 power minus 5. So, Rm comes out to be 2.866 into 10 power 9 meter inverse, straightforward, okay. So, similarly for solution, this equation we know permeate flux is nothing but delta P minus delta pi by Rm plus R gel. So, permeate flux is also given 150 liter per meter square hour. So, that we converted into the meter per second like this. Now, delta P it is given 2.1 atmosphere, in Pascals it is 2.2287 into 10 power 5 Pascals, minus delta pi we can take it as 0 because it is first of all the solute concentration is not given. So, we assume that the solute concentration is very small. So, then we can take it as a kind of 0. So, then from here Rm is also known. So, from here R gel we can find it out. So, R gel is equals to 2.484 into 10 power 9 meter inverse. What we can see here, the gel resistance is not small compared to the membrane resistance. Indeed, it is, both of them are almost equal. So, whatever the membrane resistance, the same amount of resistance is almost same amount of resistance is also offered by the gel. So, gel layer one cannot avoid easily, otherwise results may be going wrong. So, gel layer resistance is also very significant in ultrafiltration. So, delta P overall is 2.1 atmosphere, but that should be delta P gel plus delta P membrane, whatever the resistance offered by the membrane and then whatever the resistance offered by the gel are there. So, across these two layers whatever the pressure drops are there, they would be added together to get the total pressure drop, as same as in cake filtration we have done, right. So, now but delta P is proportional to the flux, isn't it. So, then delta P membrane you can find it as 2.1 into 150 by 280, 150 is the permeate flux, 280 is the pure water flux. So, from here delta P membrane you will get 1.125 atmosphere. So then delta P gel you can get it as 2.1 minus 1.125, so that is 0.975 atmosphere, which is 9.88 into 10 power 4 pascals, right. Then we have to find out this layer of particles, whatever the gel layer has formed. So that is having some thickness that we have to find out. So as I mentioned, so if this is membrane, on this surface the particles are forming. So this layer, though it is very thin, so we can apply the principles of flow through packed bed, and then we can use this Kozhnik-Orman equation, that is delta P by L is equals to 150 mu v 1 minus epsilon whole square by pi s square dp square epsilon cube. Here except L everything is known. So what we do, delta P by L, right hand side when you calculate, you will after substituting all these values you will get 4.4 into 10 power 5 Pascal per meter, right. Now delta P is also known, so L should be delta P divided by whatever this 4.4 into 10 power 5 is there, that when you do you will get L as 0.224 meters. So 0.224 meters thick particles are forming as a kind of gel layer. So gel layer thickness is nothing but 0.224 meters. It is very significant one. So finally we see the partial rejection of solute. So we have seen there are three cases: permeate flux, and then percentage of rejection, and then solute, concentrate and retentate are the kind of three important things which describe the performance of ultrafiltration membrane. So permeate flux we have seen. Now we are going to see the partial rejection of solutes. In general, membranes whatever we select, they have the pores which are larger than the solute molecules in many ultrafiltration applications. So because of that one, only partial rejection takes place. It is not possible to get a kind of complete rejection in general. So fraction rejected R is sometimes defined using the feed and permeate concentrations as RF is equals to 1 minus Cp by Cf. But the Cf we have seen in, especially in ultrafiltration membrane, it is very much different. It is very much different from one location to other location, especially that the boundary layer that is forming because of the concentration polarization. The concentration varies from C1 to Cs. So feed concentration C1 we cannot use, Cs we in general we do not know. So what happens, people in general use retentate concentration. So that is 1 minus C2 by C1 is as a kind of R rejection. C2 is nothing but the permeate concentration, C1 is nothing but the retentate concentration. Terminology is different here. Okay. So C2 is permeate concentration and C1 is the retentate concentration here, not the feed concentration. Okay. And then R depends mainly on ratio of solute size to pore size, which determines the partition coefficient, and ratio of V by Kc, which determines the concentration polarization effect. Both are very much important factor in ultrafiltration. So we have to bring in those factors here. So now whatever the equation number 6 to 9 we have, so if we combine, then we can get Cs concentration like this. How we get? We do this one. So equation 9 we just now seen R is equals to 1 minus C2 by C1. So from here 1 minus R is equals to C2 by C1, or C2 is equals to 1 minus R multiplied by C1. And then equation number 6 we have already derived. So this ln Cs minus C2 by C1 minus C2 is equals to V by Kc. This we have already derived. This is equation number 6. So now what we do, we take exponential either side. So then we get this one, and now from here, from this part C1 minus C2, what we do, we take C1 common, so that we have 1 minus C2 by C1, rest everything keep same. So now this 1 minus C2 by C1, what we can write? We can write it as R from equation number 9. So whatever the C1, R is there, that you can take it to the right hand side. So Cs minus C2 is equals to C1 R exponential V by Kc. That is Cs is equals to C2 plus C1 R exponential V by Kc we can write. And then from equation number 9 we can also write C2 as 1 minus R C1. So in place of C2 you substitute 1 minus R C1, and then plus C1 R exponential V by Kc is as it is. So, now from these two terms, if you take C1 common, then Cs is equals to C1 multiplied by 1 minus R plus R exponential V by Kc. So, this is what we get. So, that means if you know the retentate concentration or if you know the feed concentration, you can know the surface concentration or solute concentration at the membrane surface through this expression once you have the V, Kc and C1 information along with the rejection. So, if the diffusion in the membrane is negligible and solute is carried through the pores by permeate flow, permeate concentration is the same as that in equilibrium with the Cs, that is C2. That picture we have, right. So, what we have, like this membrane surface we are having, right. Now, here the particles are being deposited as a kind of gel layer on the membrane surface, right. So, this is Cs concentration, right, but other side C2 concentration is there. Okay. So, within the Cs, just inside Cm is there, okay, just outside of the pore, let us say in this pore here it is Cm, here is there, and then C2 is there. So, this C2 and then Cn, the Cs are in a kind of equilibrium, right, because they are just either side of the membranes. One is the just one side of the upstream side of the membrane, another one is the just downstream of the membrane, and then within that membrane thickness layer the concentration variations are some variations are there. So, that variations can be represented by the equilibrium partition coefficient, and then how we can represent that C2 is equals to Kcs, C2 is equals to Kcs. Now, if you use this one in equation number 11, then we get this expression for the rejection. Okay. How we get? So, that also we do it here. Just now in equation number 10 we derived, okay. This equation, what you can do, C2 left hand side we have Cs actually. In place of Cs, let us write C2 by K from equation number 11. That is the first step you do, right. In place of Cs you write C2 by K. Then next step what you do, this K you take to the right hand side, and then this C1 you bring it to the left hand side. So, left hand side you have C2 by C1 is equals to K multiplied by whatever the remaining step remaining terms are as it is. Now, C2 by C1 is what? From the equation number 9, that is rejection definition, is nothing but 1 minus R. Okay. In the right hand side you can just write it as a two terms, K into 1 minus R as one term and another term Kr exponential V by Kc, both the terms are addendum as here, just expanded it. Now, this equation what you do, both the sides you divide by R, both the sides you divide by R. So, left hand side you have 1 minus R by R is equals to, right hand side we have K 1 minus R by R plus K exponential V by Kc, because R and R from the second term would be cancelled out when we are dividing it, right. So, now what you do, this 1 minus R by R terms you take one side. So, then you have 1 minus R by R multiplied by 1 minus K in the left hand side, and then right hand side K exponential V by Kc there in the right hand side. So, we can write 1 minus R is equals to K by 1 minus K exponential V by Kc. This is what we have. Okay. So, now from this equation, when this V by Kc approaches 0, V by Kc approaches 0, then what we have, exponential of 0 is 1. So, that means rejection approaches 1 minus K, rejection approaches 1 minus K, and then rejection decreases with increasing flux because of the concentration polarization. Further, in this kind of expression whatever we have found, they are found to be kind of reliable in ultrafiltration of a dilute dextran solution using a tubular membrane. Rejection varied from 77 to 93% with decreasing flux experimentally, and it is found in good agreement with our equation number 12 just we derived when by substituting K is equals to 0.044. But in general, what happens in the layer for filtering solutions of moderate to the high concentration, maximum flux is in general low, and then diffusion in pores may become important. In some cases, it is possible that the diffusion in pores is much more dominant than the other cases, right. Under such conditions, how these equations would change. So, now in the previously whatever the changes were there, the concentration changes, those things we have seen in this side, right. So, but now this membrane layer, within this membrane layer, selective layer, it is having certain thickness, maybe in some microns, but it is having certain thickness. In this thickness, there are several pores are there. In the pores, if the diffusion is dominating, right, that part we have not taken care while deriving the concentration polarization. So, under such conditions, what could be the equation for the Cs and V, etc. So, again we have to see the basic equation here, basic balance equation. Now, what happens here, the diffusion is inside the pore. So, then at the membrane surface, whatever the flux is there, that is the flux is only because of the convection if you take. So, that convection is Vc, and then other side the flux is the Vc2, and then that should be added with the flux due to the diffusion inside the pore. So, that is dE dC by dy. So, dE dC by dy should be added here. So, that if you take into the left hand side, you will get this one, right. And then dE is nothing but effective diffusivity, that is d pore epsilon by tau, and then y is the distance from the membrane surface towards the permeate, from the membrane surface towards the permeate, that is in the y direction, the reverse x direction. So, that is y here. So, at the membrane thickness is L. So, y limits are, limits of y is nothing but y is equals to 0 here, and then here y is equals to L. At y is equals to 0, C is nothing but Cs. At y is equals to L, C should be C2, but they are having some partition coefficient, equilibrium, they are in equilibrium with each other. So, then the corresponding concentration should be multiplied by the partition coefficients k, right. So, now this equation will be integrating and then applying the boundary condition exactly the same way that we have done for the concentration polarization. Then we have V terms if you take one side, and then D terms if you take the other side. So, then V C minus C2 is equals to dE dC by dy, then V by dE dy is equals to dC by C minus C2. When you integrate it, V by dE, integration of dy is y, and then limits are 0 to L. 0 is the membrane surface, L is the membrane thickness towards the permeate side. Okay. So, right hand side ln C minus C2 should be the this thing, after the integration of dC by C minus C2, you will get ln C minus C2. That limits at y is equals to 0 is the membrane surface towards the feed side. So, that is at the membrane surface, on the top surface the concentration is Cs, but now we are assuming the partition factor for both the boundary layers of selective layer are there. So, then K has to be multiplied. So, KCS, and then towards the inside the other side of the pore. So, that is here in this pore, this side. Now, this is the layer actually. This is your thickness of the membrane actually, L. Okay. This side the surface concentration is Cs, this side moment it comes, this side other side it is C2, but it has same partition coefficient, that is the assumption, because we do not know exactly what is Cs, we do not know exactly C2 inside the pore. Okay. So, they are in equilibrium with a kind of partition coefficient K. So, that has to be multiplied here. So, when we take these limits, then VL by dE is equals to ln Kc2 minus C2 divided by Kcs minus C2. Then you take exponential. So, here K minus 1 C2 by Kcs minus C2. When you rearrange this equation and then do the simplification, you will get Kcs exponential VL by dE minus C2 exponential VL by dE is equals to K minus 1 C2. Further, you take all C2 terms one sides, Kcs exponential VL by dE is equals to C2 exponential VL by dE plus K minus 1 C2. This equation, if you write C2 by Cs form, right. Then we have k exponential VL by dE divided by k minus 1 plus exponential VL by dE. This is what we have this equation for a surface concentration if the pore diffusion is predominating. If the pore diffusion is predominating, under such condition the surface concentration on the membrane surface can be obtained by this expression, or the relation between the surface concentration and permeate flux can be written as this equation number 14. So, L is the thickness of the selective layer, that membrane thickness. If VL by dE is less than 2, then the solute diffusion will have a significant effect on the rejection, and then VL by dE value goes further beyond the 2, it is going to have a pore diffusion is going to take the lead. Since the diffusion lowers the rejection at low permeate flux and concentration polarization is important at high flux, fraction rejected is predicted to go through a kind of maximum with a permeate flux. References for this lecture are given here, but most of the notes is prepared from this first reference book, McCabe, Smith and Harriet, Unit Operations of Chemical Engineering. Thank you.